All right, hello everybody. I am Reed. I'm going to talk to you about processing structure and properties of compact bone today. So, this begins the start of the presentation where I tell you what I'm about to tell you. And then I'm going to tell you what I'm going to tell you this whole time. And then I'm going to tell you what I told you. So, starting with a light overview, we're going to talk about the bone deposition and resorption process, the structure of bone, and the material properties of bone. So, bone production, pretty interesting process here. So, osteoclasts are these cells that are responsible for taking away bone, destroying bone, old bone, and what they do in this process is they release the ions that are inside of the bone, inside of the crystals, calcium, phosphorus, and they release them back into your blood to help maintain homeostasis and ion concentration. Osteoblasts are another form of bone cell, except they make bone. And the way they do this is they secrete collagen down. The collagen self-assembles and is then organized into a plywood-like stacking fashion and wrapped radially around blood vessels, as seen in the upper diagram on the right-hand side. The osteons is the structure I'm describing right now. And then another job that they do is they also mineralize the collagen that they lay down. And they do so by secreting proteins such as osteopontin. Osteopontin, the general theory in the biomineralization community is osteopontin gathers calcium and phosphorus and ions necessary for the biomineralization process, and then concentrates them into a metastable liquid-like secondary phase in your blood, and then slowly deposits these liquid-like phases onto your collagen, and then through interactions between the collagen and this amorphous liquid-like calcium phosphate crystallize and give us the great composite that is bone. So looking a little further into the two components that I mentioned there, collagen and hydroxyapatite, we'll start with collagen. Collagen is made up of amino acid chains. One collagen molecule is 3 amino acid chains, 2 alpha-1 helices and 1 alpha-2 helice. When you have a lot of those collagen molecules called tropocollagen, you get them bound together. They're called fibrils, collagen fibrils. And then when those fibrils assemble further, they're called fibers. And then those fibers are then organized into sheets, plywood stacking, and thus the structure of your bone. Now, when collagen fibrils are made, they're about 100 nanometers in diameter. And the way that tropocollagen stacks together in these fibrils, they form a little gap in between the C and N terminus of these collagen molecules. And the gap there is consistent across collagen. It's almost always about 40 nanometers. And we see it very easily in TEM with a phenomenon known as banding, as you can see with this middle image. And then the image on the far left is an SEM image I took of some collagen that I made from a rat collagen solution we purchased. And as you can see here, these are what we would call collagen fibrils, aside some what looks like amorphous collagen. Now looking at hydroxyapatite, remember I mentioned that that gap region is about 40 nanometers. That gap region is generally where we find hydroxyapatite. Hydroxyapatite is this calcium phosphate crystal. It's what gives bone its strength and its stiffness. And these crystals are about 60 nanometers long. Now, I'm mentioning that for a reason, because people in the biomineralization community have been that was a question that was kind of in need of some reconciling. How are these crystals bigger than the holes that they occupy? How are they bigger than the spaces that they're supposed to get through to get there? And this is what came up with the theory that osteopontin is gathering it and producing this liquid-like metastable phase that can be deposited onto the collagen and then subsequently mineralized inside of the gap region of the collagen fibrils. This is the working theory, at least, for many in the biomineralization community. So focusing more a little bit on the properties of bone that we get from that really cool interaction between crystal, protein, and collagen, we get a great strength to weight ratio. Just looking at a general look at this diagram, this table, you can see if you divide yield strength by density for cortical bone, compact bone, you get about 50, and then you do the same thing for stainless steel, you get somewhere between 20 and 35, both lower than bone. That's great. That's a really great and interesting property to have. As well as being stiff, they're also tough and elastic. And so collagen imparts a lot of elasticity into bone. It's not insanely stiff. The apatite crystals give it a lot of that stiffness, and it also has the property of being a self-healing material in the sense that osteoblasts and osteoclasts come in and resorb and deposit new bone and are constantly making new bone. One other interesting thing to mention about this self-healing process is the concept of the piezoelectric effect in bone, which is, I would like to think of as another property of bone, is its ability to thicken over time. As many athletes know, after years of training, a lot of times bones get thicker in people. And it's theorized in a number of papers, one specifically, this one shown on screen, Robbie 2012, is that this is due to the piezoelectric effect. As bones are compressed, the collagen molecules in them are also compressed. These collagen molecules have charged groups on the outside. When they are compressed, these helices get unraveled in a sort of way, and then these charges are then exposed to the solution around, and this presents some sort of signaling to cells to come in and resorb and grow more bone, depending on tension and compression in your bones. So this is another great example of material property of bone. So that concludes the portion where I tell you things of my presentation. This is where I tell you what I just told you. So we just talked about how the relationship between structure, processing, and properties in bone are heavily related to our two structural components of collagen and hydroxyapatite, and the non-collagenous proteins, osteopontin, that facilitate the deposition of this mineral over space and time and how it happens. And there are also fundamental questions about the exact mechanism behind the formation of apatite crystals in the collagen matrices of bone. This is still being studied. Thank you so much for watching. I have had a great time in this class. Dr. Samsira Wong is amazing, and so are all of you. I hope I see you very soon. I know I will. All right, bye-bye now.